Hi everybody, my name's Joel. It's not James. James is the track host and owner, but he said, Joel, you should step in and introduce these guys, so I will. How you can tell the difference, despite the fact that we have the same, or very similar funny accents, rugged good looks, black hat t-shirt, purple shirt, kind of beer gut on me, so that's how you can tell. My job is actually really, really easy. I get to spend 5 minutes setting context for the two talks that you're about to hear. It's all about the server side, what we do for Facebook's kind of server-side stack, both running code on and in our data center and the programming model. So there are two pretty exciting talks by two of my colleagues, very fond of them, Julien Verlaguet, who is one of the Hack founders, and Ed Smith, who has been on the HHVM team for quite a number of years. But to start with all of this, I should ask you a few questions. Who has actually heard of HHVM? Oh man, that is awesome. I love it. That's great. How about Hack? Great. Love it. This is perfect. I don't have to do much. This is great. I can just get off stage quickly, go drink some beer, and I'm done. Actually, who is here for the free beer? Wow. Okay. Very few of you. All right. Well, it's on me this afternoon. So purple shirt, I will shout you a beer. Happy to. Okay. So for those of you who don't know what HHVM or Hack is, we'll start with HHVM. And HHVM is quite simply a PHP virtual machine. So if you've used Java or C# before, both of these languages run on top of kind of abstractions, virtual machine abstractions. The JVM for Java, or the Java Virtual Machine, and the CLR for C#, or the Common Language Runtime. HHVM is like a synonym for that, for PHP, and also Hack. And the reason we did this largely comes down to PHP's inherent dynamic language nature. Dynamic languages, at least until a couple of years ago, were kind of seen as a bit slow compared to their static language counterparts. But we've seen a lot of innovation in the past couple of years to really speed them up with V8 and, of course, for JavaScript. And for PHP, we've done it with HHVM. And it largely comes out of this. This picture is of one of our data centers in the early stages of the build. And when I show this picture to people, I really like to say, whoops, wrong way. I really like to say, look at the tiny little truck. And then look at the building that's behind it. Massive, massive data center. And you walk into this data center, like the HHVM team did probably 3 or 4 weeks ago, and it is mind-blowing. And Ed's talk is about how HHVM fits into that data center story. It's quite amazing. So Ed will walk you through what the HHVM team does for its core mission. And its core mission is to take PHP and Hack and run it as fast as possible on these machines in these data centers. And this is a picture of inside the data center. This is Headstand Abby, one of our colleagues in Boston. She has a great blog where she takes pictures of herself doing headstands in exotic locations. Great picture. The stuff on the side is actually also really, really interesting. You walk down the data halls and you see like all of these open compute web servers that are running HHVM, and they're taking air in, computing bits, and pushing hot air out, and it's great. Okay. On the Hack side, Hack is quite simply a new language based on PHP that we're using at Facebook internally. And its story is born out of this graph. I mentioned before about dynamic languages and their performance. One of the other things that dynamic languages are really, really good at is iteration speed. So when Zuck was in his dorm room back in 2004 or 5 or whatever it was, he chose PHP to sit down and rapidly hack out Facebook.com in the early days. And this served us really well because it has an excellent iteration cycle. You open up some code, you furiously type into your editor, you hit save, you hit F5 in your browser, and bam, your change is there. So you can kind of rapidly iterate and create your kind of whatever fantastic web property. This works great until the kind of graph of the amount of engineers or the amount of teammates that you have kind of starts going up and to the right. We have about 1,000 engineers committing code to the www front end, so www.facebook.com. And of course, that means a lot more code gets generated, meaning also that you can't really internalize all of the code that's being produced. So you start to then think, well, I wouldn't mind borrowing some features from the static language counterpart, from Java, from C++, from C#, and so on. Static languages and their type systems have really great properties for kind of establishing invariants on code, for documenting code, and so on. I mean, you know the deal. The problem with them is iteration speed. I'm sure there's plenty of people that have hit the compile button and then gone off and got a coffee because it's just too bloody slow. Come back, compile may be done. If it is, great, make a change, hit the compile button again. It totally sucks. So Hack is born out of trying to keep the rapid iteration cycle that you have with PHP, but then borrow from the kind of static world, but not sacrifice iteration speed, as in have 0 time compiles. That's great. So that is the context for these 2 talks. They're pretty damn amazing. As I said, love to chat with you guys at the end and after the talk later in the day. Free beer on me. Or actually, maybe Uncle Zuck. But yeah, give it a round of applause for Julien.
Hi everyone. I hope everybody can hear me. Yeah, everybody is fine. So, first I'd like to start with a story, actually. And in fact, I call it a story. I'd like to say it's a bit more of an adventure, because to me, what this project has been to me is really an adventure. So the way it started is that 2 years ago, I was in a completely different team doing something completely different. I was working in security infrastructure. And what this team is doing is it's trying to build infrastructure in such a way that programmers are shielded from security problems. So it can mean, building a good library, it can mean building a good abstraction. This can take many different forms. And so while I was more specifically focusing on static analysis back then, and we're looking at PHP code, and I was working with Alok Menguajani, a co-worker of me who started the project with me, and we were looking at the code and thinking, well, what the problem is that we lack some information. We'd like to build some tools that look at the program and that could just tell us more about the intention of the programmer before we even run the program. And so somebody said, I don't remember who, something like, well, it's easy. All what we have to do is take the Facebook PHP stack and rewrite it to a statically typed language. Right. It's easy. Right. And after 2 years, I think that this is exactly what we've done. So I still think it was crazy, by the way. If you ask me even today, 90% of the code base is in Hack, and people use Hack every day, and I think we've been successful. But I still think that it was a crazy idea to engage with in the first place. And so without further ado, I'm just going to start talking about the project itself and what this looks like, basically. All right. So yeah, first, before I get to my demo, I really want to show you the code, that's why. So as Joel has mentioned a bit of that already, but what's happening is that there's a divide in the programming world, right? There's a divide between the dynamic world and the static world. So here I picked a random PHP developer who was trying to build something in 2004. And what he was trying to build was an experience. So an experience means that it has to feel right. So it's not about passing unit tests, right? It's about using the product and interacting with it, and it has to feel right. And for this to happen, there's only one solution: you have to iterate. And for that, PHP is doing a great job. You modify your code, you press enter, you press refresh, and it's right there. So you can iterate on the experience and make it perfect. Now, I'm going to pick another random developer, but this guy is doing C++. You might have recognized him. And this is the static world. So the static world is very different. And I picked C++. I could have picked Java, C#, you name it. That's not the point here. But in C++ specifically, what it's about is it's about squeezing out as much CPU as you can from the machine, right? So you're writing a back-end service that is, I don't know, doing routing or whatever it is. You don't care about the experience, right? That's not how you measure these things. So if you look at these two worlds, they are so different because they care about different things. However, there are things in the static world that we still need on the other side, right? What we wanted on the PHP side was the type checking, was some feedback on what this value actually is. And Hack is trying to reconcile the two. Take the best of this side and bring it into that world. So now I'll show you some code. I was looking forward to that, so it's finally happening. Okay. So let's write a file. So I'm going to write a very... Can everybody see? Oh, this one is off. This one is good. Okay, is this... Should I just... Yeah, 1 second. Ah! Okay, well, look at this one. Sorry about that. So I'm going to write a very simplistic file, which really doesn't do much, but it's more to show you what this feels like. And so what I'm going to do is introduce a typing mistake on purpose. So here I built a variable $x that is a string, and I added an annotation here. This is how you annotate a return type in Hack. And I said that it was an int. So obviously there's a problem here. I'm returning a string while I said that I was going to return an int. And so there is one command that allows you to do the type checking. It's called HHClient. So I run this command, and I get an error. And I could just, take this code, take these lines, and go figure out what it means. But that's not the way you're supposed to use it. The best way to use it is use the editor integration. So whether you're using Vim, Eclipse, Emacs, Sublime, whatever it is, we have a plugin for it. And if we don't, we'll build one. So what it is about, why it's better in the editor, is that you can navigate in the code. So Hack errors are a bit bizarre. The way they start is by pointing you to where the problem is. So here in that case, it's telling you invalid return type, right? And then the rest of the error is hinting you to what you should fix to make that error go away. So in this case, it's telling you that this is an int, and it's incompatible with a string. And it's pointing you to the string. And in that case, it seems obvious, but you could have a lot of code here, and it could take you a while to figure out where the incompatibility in the type comes from, especially if it's across multiple files. Now here, I can just navigate, go where see where the error is, and then look at the places that are incompatible. All right. So I'm just going to remove this file for the demo and go back to my slides. Do I have to press the button? Yes, I do. Sorry about that. So I've shown you very briefly what Hack looks like. So what is it, really? That's a very legitimate question. What it is, the best description you can get is a statically typed language for HHVM. HHVM is what Joel was just talking about earlier. It's a JIT runtime. Now, there are some specifics of it. So first of all, it's compatible with PHP. What that means more specifically is that from Hack, I can call into PHP, and PHP can call into Hack without any overhead whatsoever. There's no stub code, no API, no, there's nothing you have to do. You just write the name of the function. Then, another important aspect of it is that it was designed for incremental adoption. So what that means is that you're not forced to write all your code in the statically typed world. So you probably come from languages, I'm just speculating here, but how many people know Java in this room? Okay, everybody knows Java, good. And so Java, C#, and these kind of languages are fully statically typed. So what that means is that if you don't write int x, it just doesn't compile. You're not going to run your code, right? And Hack is different in the sense that you can choose how much you want to annotate your code. So you can start prototyping and saying, okay, right now I don't care about types, right? I'm just going to write my prototype. And then later on, incrementally, you can decide for yourself to go and add type checking to a file if you want to, but you're not forced to. Oh yeah, the types. See, I always want to write code. Natural instinct. So what I wanted to say here is that the type system is actually pretty rich. So some of you, well, everybody knows Java, so we have introduced collection with generic types, so that looks very familiar, I would assume. One very interesting one is the nullable type. So we can prove, by default in PHP, nothing can be nullable. The type checker is going to enforce the fact that values cannot be null. So you cannot be bitten by a null pointer exception by mistake. Actually, you can if you haven't annotated your code and your code is dynamic, but that's a different problem. So this is one of the most interesting ones, which is different from what you're used to. But without further ado, oh yeah, oh God, sorry. I want to go back to that machine. So what must be annotated? Because this is a bit different from what you guys are probably used to. All what you have to annotate in a nutshell are the parameters and the return type. And all the rest is inferred, right? So what that means is that you don't have to write int x equals 0. You just write $x equals 0, and the int part is inferred. It's guessed by the type checker. Now, that's kind of interesting, but I'll get to that later. It's about the modes. So, as I said earlier, there are different levels of flexibility in the type system. And so that means that we have different modes where you can say, I want to check everything, and that's strict mode. So you have the option to use Hack as if it was a fully statically typed language if you choose to. And that's just by putting strict at the top of your file. The default mode is partial, and that allows you to mix dynamically typed and statically typed code. And finally, the last one is decal. It's more for external APIs, so I'm not going to say much more about this. Now is the demo. Yeah. All right. So what I want to go through very quickly is show you how you can mix dynamic and static code. And in fact, I have an example ready that is a very simple data structure. So I wrote a class here. Even if you're not familiar with the syntax, it should be close enough to what you guys know, right? Oh, yeah. So this is a mailbox. And a mailbox, it's a data structure that you can send data to and fetch data out from, right? So it's just a basic object that contains data that you can send to and fetch from. Not much going on. The first step is saying that we are now in HH. And now I run the type checker, it says no error. And that's going to happen a lot. You are often going to have PHP files that appear to be valid hack code. And so let's start annotating things. So this looks like a string. It looks like it's returning void. And I can stop here. I have no error here. And I could just say, well, I've done my job for today. I don't want to work more on this file. And you already have static guarantees on the parts that you annotated. So here I will get an error on send because I did have an annotation in here, right? Now, for the sake of the demo, let's try to finish it and actually annotate the entire thing. All right, and this works. And I said earlier that there is a mode where you can say, I want everything to be checked, and I want to make sure that nothing slipped through. So let's put strict in here. And here it's going to complain. It's complaining about this function because this is a PHP function that lives outside of the hack realm. So you can go over where that function is defined and convert that code to a hack if you want to. Or you can just, well, in that case, I'm going to remove it. Or you can stay in partial mode if you're happy with that. All right. So now I said earlier that there was a null type, and I'm going to initialize with null because this is what we do most of the time. We don't initialize with empty strings, right? And so here, you now have a string, and this string has to be a question mark string because you have to say specifically that something can be null. So I'm going to go ahead and annotate the type of the code with a question mark. And so in this case, I could carry on like this forever and add question mark string everywhere, but eventually I really want to use that thing as a string. And that's when I check if my string is not null. And if my string is not null, and I did check it in my code, then I'm actually, so I need a default value here. So when that's the case, the type checker actually picks up the fact that you did a check. So within this branch, it will let you use $msg as a string because you did check the fact that it was not null. And after all, that's what most people write naturally, right? This is the natural way to deal with something that is nullable. Now, to take a step a bit further, this class could really work with any type. So I'm going to make it generic. And there are two things I want to show you about this generic example. The first one is that here, I didn't have to write mailbox of string. This was picked up directly, automatically by the type checker. And another thing is that if I introduce an error, the witness system that I showed you at the very beginning is going to be very useful. So I save here, and it's going to tell me this is an invalid return type. You tell me it's a string, and you've given me, you tell me it's an int, and you've given me a string here. And it points you to the place where it deduced that this mailbox was in fact a mailbox of string. That's very useful when you have a large code base and it's not always easy to figure out what the type of things are. Okay, but enough of that. And let's go back to my presentation. All right, so what I've shown you so far is mostly in this world, right? Remember there was a dynamic world here, there's a static world here. Most of what I've shown you is the static world applied to PHP, basically, in a nutshell, right? And a fair question is, well, why do I care about this, right? A fair question is, a fair observation could be, well, you've just reinvented Java, but worse, right? And that would be fair, right? And I would like to say that the reason why this is different, I could talk about it for hours. I can't. The only way I can show you why this is different is by showing you. So again, I'm going back to my computer that I love, and I will show you why this is different. So here I made a large directory with 1,000 files. These files, they don't do much, so I'm going to show you one example of it. But basically what they do is that they call a method called bar, right? And there are 1,000 of them, right? And now I'm going to go where the method bar is defined, and I'm going to change the type of this thing to string, let's say. And I run the type checker, and here we go. 7,000 lines of errors absolutely instantly across thousands of files. We get less than 200 milliseconds response time on multi-million line code base. Now, let's actually measure the time it took. So I'm going to put a time in front of it, modify it, 98 milliseconds to recover. Now, let's take it one step further. So if you're like us, you use Git or Mercurial or any of these revision control things. Now, I made a branch here that removes all the examples in the directory, right? So what I'm going to do is go in master, introduce the error that I introduced earlier, right? The errors are here. And I'm going to measure how long it takes if we check out remove examples and all the files are gone and give me the state of the world. And that's just 64 milliseconds. So even if you are using revision control, checking out many directories, going from one branch to another, it will always be responsive. You can always hit that thing. And so the magic behind it is basically that there is a demon that is constantly watching the state of the world and keeping everything up to date all the time. Now, what I'd like to do is give you a sneak peek of where we're going with this, right? I showed you Emacs, I showed you a terminal. Well, maybe we want to go even further and make the experience for a developer with less friction. And developers are used to work in a browser, right? So here, I just want to show very quickly where we're going with this. So we took the front end of Hack, compiled it to JS, and built an entire IDE around it. So here I can show you that you get autocomplete directly all in your client. And that's why the responsiveness of it is so good. And you can get, hover over things, all the things that you would expect from a normal IDE, all working in your browser right there. All right. Now let's go back to... So finally, I'd like to say a few words about Hack, the project, where we are, and where we want to go. So we open sourced Hack around a month ago. All the information is on hacklang.org. And I'm actually really excited about this. What I'm excited about, so when Hack came to be and when we were converting Hack, the www code base to Hack, basically what we needed to do was interact with a lot of engineers. We needed to, there was no management involved, right? The decision to switch to Hack was engineers adopting that technology, period, right? And so there was a lot of talking, a lot of exchange, and I learned a lot from that. From engineers telling me, well, this sucks, this slows me down, I don't like this. And yes, feedback that comes in the form of this sucks is actually useful too. You know that there's a problem, right? And so the reason why I'm so excited about open source is that we can carry on doing that at a much bigger scale. We now have the entire world that can give us feedback, that can help us. We can build a community around it that is going to help us shape the future of this project, really. And that's what I'm excited about. And thanks for your attention, and that's all I have. Thank you.
Awesome. Thanks, Julien. I'm excited, too. It's HHVM running that. That makes me excited, to build a PHP engine and have it running a new language without having to do very much. All right. So my name's Edwin Smith. I love building compilers and virtual machines for dynamic languages. Before I worked on PHP, I worked on another language called ActionScript, which was derived from JavaScript, which you heard so much about already. It's just something fantastically interesting about looking at a dynamic program while it's running and finding the interesting static program that's running inside of it, getting rid of all the extra overhead of dynamic and letting the static program stand out. That's really what we're doing. Basically, I'm going to walk you through how we tune PHP. And to understand how you tune PHP and how to make PHP run fast, you have to understand what it's doing. And what PHP is doing is handling web requests. And there's a bunch of stats here about how big the web requests are and how often they come through. But we're basically just going to walk through what it's doing. And then I'm going to walk through how a machine reacts to what it's doing. Like, what does the CPU actually do? And then give you a little insight into some of the things that we've done. So when a web request comes in to a web server, the web server is already up and running, ready to handle it. And there's some code already in the web server ready to handle it. And a person comes along and makes a web request. And you get an initial heap. You basically have some information about who's making the request and what are they asking for, and it takes up some memory. Then you do some querying of a database, or hopefully if you have a lot of data, you need to put some cache in place. And so you do some querying of your cache, and you do some more querying of some more backend services, and you're basically putting together like a whole package of information that you're going to send back to the phone or the web browser. This takes a fair amount of data fetching and processing to send it back. And you see this request heap getting bigger and bigger, and in order to process all that data, you've got to get it into the place where the processing actually happens. And so I want to sort of help you understand the perspective. I'm not going to tell you like in gory, boring detail how we do this, but I can afterwards if you want. But I want to give you kind of like my perspective of what's going on here. You saw the data center picture earlier with the big, giant building, and you saw Abby sitting in the data center, sort of becoming one with the machine. We're going to become one with the machine right here in this room. And Mario Andretti said that you don't have to know how a race car works to drive it fast, but if you have some sympathy for what the car is experiencing, you can actually drive it faster. So we're going to have some sympathy for the underlying machine. So there is a computer. And what a computer consists of is a lot of plumbing. There's very little computering going on in a computer. It's all plumbing. You know, ever since I got started working on computers a long time ago when I was a kid, like a lot of you, I wanted to be able to go inside of it. And I never could because I was too big and the computer was too small. Now we have big data centers. And if you go to a big data center and walk inside, you will have this profound experience of going inside the computer. So what we're going to do is go inside the computer here and have some sympathy for what's going on. When you walk inside a data center, it's hot, it's noisy, it's really big, and there's this giant building, and there's power and cabling and everything, but you ask, where's the computer? And you can go into one room where there's a computer, but around the computer is this vast network of stuff that just feeds all the requirements into the computer. Feeds data in, gets data out, feeds power in, blows hot air out, gets air in, gets air out. You know, there's all this plumbing that's just all there to serve the computer. You can walk around in it, you can look and put your hand on a computer, and you can look over there and see a database, and it's really cool. It's like you're inside the computer. So this is the inside of a CPU here. What you see is all plumbing. It's a multi-core CPU with lots of memory and lots of cores, and inside those cores there's more memory, and the actual computation is just very, very, very small. It's the same as in a data center. And so to go inside, we have to have an appreciation for what time is like. You didn't think you were going to hear a lecture about time and space and relativity, but here you are. Put things in perspective for a second. Speed of light. Does anybody know what the speed of light is? It's about 300 million meters per second. And so as I'm talking, we're clicking off seconds, and light is going 300 million meters around. And if I want to know anything, the limit of something I could know in 1 second is the distance. I could know something about something that happened 300 million meters away. But computers are operating on a different time scale than we are, and so their distance shrinks along with time. So let's just sort of like walk through what this is so we have a good mental picture. A millisecond is 1,000 times smaller than a second. This is the time scale that networks operate on. The distances are smaller too. 300 million meters per second is now 300,000 meters per second, right? We're starting to feel a little bit more global and less university. Light actually has can't really go that far in not very many milliseconds. But basically, like, think of a millisecond as like the time scale of the network and the packets. You know, when you send a packet, you might get another one back in a millisecond, hopefully, but maybe more milliseconds. Really fast network might be less than a millisecond, but this is the networking time scale. You want to feel what it's like to be in a network. Packets are going by like once a second, right? And if you have to wait a whole second for something to happen, that's really like 1,000 seconds, right? So it's like set your watches and wait 15 minutes to get a 1 second answer back from a network somewhere else. A second is just like painfully long for a network, right? Millisecond is where you want to be. But computers are way smaller than that and way faster. So microsecond is 1,000 times smaller than a millisecond. This is the time scale of memory, basically. SSDs, DRAMs, they're plus or minus on the order of microseconds. This is 1,000 times faster. So a network packet is like painfully slow to wait for if you're thinking about memory, right? Memory's happening really fast, network's really slow. Talking to a user and getting an answer a second back is like we're basically off the charts. We're ready to go take a nap and come back. Again, distance is also interesting because 300,000 is now 300. 300 meters is how far light can go. If you want to know something in a microsecond, you cannot know it. It's beyond the capabilities of the universe, the speed of light. You cannot know it if it's more than 300 meters away. 300 meters is like, not much bigger than the end-to-end length of this room. So if you put your database more than 300 meters away, you will not get an answer in 1 millisecond. It is impossible. The laws of the universe prevent it. But that's also not the timescale of the computer processor. The processor is at a nanosecond timescale. That's 1,000 times smaller than a millisecond. In terms of distance, it's not 300 meters, it's 0.3 meters. This is 1 nanosecond. This is how far light travels in 1 nanosecond. If you want to know something and you want to know a nanosecond later, it can't be any farther than this away. You can't put a register over here and a computer over here and get an answer in 1 nanosecond. It just can't be done. So you have to put them close together. And this is why computers that are really fast need to be really small, because at a clock cycle of 3 gigahertz, that's 1/3 of a nanosecond. That's 0.1 meters. That's this far. That's the length of my finger. So the little chip that's the size of my thumb, and the 1 clock tick later, the data it's trying to access, that's it, right? Anything beyond that, the horizon of the knowable possible information is gone. So it's really small. So this is mechanical sympathy. You've got this poor little computer living in a bubble that's only the size of your hand. Anything outside the size of your hand cannot be computed on. You can't even know about it in 1 clock tick. And there's actually a lot of transistors that are all waiting on data 1 clock tick away because we can't speed up things. We have to do more in parallel. So this is the world of the microprocessor is a very, very tiny world. I mean, I'm not even going to try to make an analogy for what a 1 second turnaround time is for a computer, right? It's basically shut it down, go to sleep, wait for dinosaurs to expire, wait for continents to shift, and then, you know, an answer comes back 1 second later. Like the processor is just stopped cold in its tracks. So if you want your really cool, fast computer to actually be busy and not be stopped in its tracks, you have to put data close to that little computer. So you have a processor, you have some data, it's not close enough. 100 nanoseconds is really far away. You also have dozens of cores. They all want data. So we're going to take some cores, and in order to keep them busy, we're going to put some data really, really close. The first level of cache is really close to the computer, and it's 1 nanosecond away. So that's already 3 clock ticks. So you better have enough work to do that takes 3 clock ticks, or else you're going to stop and wait for data. I'm talking about performance tuning, but this really applies to any language, any computer whatsoever. You basically have to get the data close to where you're going to do computing on it, and if you don't, you're going to be waiting. This is the whole name of the game. So we keep the cores busy. But because they're so small and so close to the computer, you just cannot put very much data in them. And if you need any more data than that, you're back to waiting again. So you have another level of cache that's bigger and slower, and another level of cache that's even bigger and even slower. 12 nanoseconds on this time scale of clock ticks is, what, 36 clock cycles? Say I have 8 functional units doing 36 clock ticks. That's 8 times 36, like units of work I could have done, but no, I had to go to level 3 cache on the chip just to get some data to work on. So that's a stupendously bad stall just to hit that 3rd level cache, which is still on the chip. Going off the chip, 100 nanoseconds, that's 300 clock ticks. That's like thousands of potential instructions you could have run, but you didn't because you're waiting on memory. And the real story here is that there's never enough cache. There's always a bottleneck going to RAM. If you go beyond RAM to off the network and somewhere else, you're just now at 1,000 times bigger time scale. It's just like forever, right? From the computer's point of view, it's forever. And so this is what the computer's experiencing. If you have a large code base and a large data set, it doesn't all fit on the chip. And so you're basically always working to get the data closer in and finding ways with your algorithms and your data structures to do that. So that's what we do. That's what we do all the time, all year round. It's just this fascinating, continuous problem of fitting data into the computer. And when you manage to fit more in, there's always more waiting to be fit in. So it sort of never ends. Like Zuckerberg's law is that we're going to share twice as much every year. And that makes me cry because like these caches are, that's faster than Moore's law. Like Moore's law is doubling every 18 months. This is only once a year we're doubling. So what are we going to do? So that's where we try to fill the gap. So to give you an example of what we've been doing, you've heard the adage that premature optimization is the root of all evil. That's true, but there's a corollary to it that I'm going to come to at the end of the talk, is that sometimes it's not premature. You still have to actually optimize, like when you've got something. But before you really spend a lot of time optimizing, you have to think about your algorithms and your data structures. And in a VM, the algorithms are in the compilers and the memory manager, and the data structures are the data structures we use to represent, in this case, PHP values. But if this was a Another language would be those values. And you saw that PHP request with all that data. It's basically all strings and arrays. And yeah, there's objects and there's components and all sorts of things, but to a first approximation, they all come down to arrays and strings. Just a fact of life. And this is what an array looked like in the early stages of the virtual machine that we're working on. What you see here is a header. It's got information about the array, a hash table with some entries in it for some values in the array. And the header points to the hash table because it might grow, and so you might have to reallocate the hash table. And then in the hash table, there's pointers to some data values, Alice, Bob, and Carol, and then are the names, and then you've got some user IDs. And so you have pointers so you can look up names, and then you also have to keep track of the order that they're in, and so you have pointers that keep track of the order. So you can iterate over the elements in order, or you can just access them using random access. Now, every one of those pointers is a piece of data that says the memory address of where some other data is. And in a large system processing a lot of data, you finally got that pointer into the first level cache and into a register, and you looked at it, and now you're in the CPU timescale. Everything you need, if you're going to do anything with that pointer, it's got to be, in this little sphere of one clock tick away, or else you're waiting. And the problem is a pointer is pointing somewhere else in memory, which is likely, because it's a big system, not in your cache. So you read a pointer, and boom, you wait. And then that's that yellow arrow. Then you go to another table, you read another pointer, and boom, you wait. So every one of these arrows is a painful, sleep-inducing, stress-inducing, power-hungry wait for data. And meanwhile, the CPU can't do anything at all. So the name of the game is getting rid of all these pointers. How do we pack data and memory closer together so that once you access it, the data that you need is all close to you and you're not following more pointers, right? We want to eliminate pointers out of this data structure so that it can be fast. Now, that may mean we have to copy data more often than before, but copying on a computer is really, really fast. You're streaming memory across a bus that's designed to handle bulk data transfer. So dereferencing a pointer is expensive, but copying a whole lot of bytes is really cheap. So we want to pack this data structure closer together. At the end of last year, this is what it looked like. You had a header and some data and the hash table all in one place. And you still had to be able to handle arrays that grow, so there's still a header and some pointers. But this is where we are now. At the beginning of this year, we were able to actually pack the header and the array together by refactoring some other parts of our code so that if you do grow the array, you just, why am I trying to save the work of copying the tiny little header when it means I have to chase a pointer? Well, it's cheaper to just copy the header every time too. So this is what happens now. You have a fully packed array, no pointers. And so if you touch that array at all, all the data in the array is going to be close by. And even if it's not all the way in the cache, it's going to be contiguous, and so it's going to page in and prefetch, and the processor is really good at handling arrays. It's not so good at handling pointers. So that we didn't just work on arrays in 2013, but that's the pattern of what we've been doing. It's the same pattern repeating over and over. So we built a new JIT compiler, a just-in-time compiler. The reason you have to work on the compiler is because you have to understand how the programming is accessing data, teach the compiler how to find those expensive operations and eliminate them. So even though we're really optimizing memory so that we can squeeze time out, the compiler is the program that we have to teach how to do it. We spent some work on strings, doing similar things that we did with arrays. And then if you think about the code in your program, it's also like chopped up into all these little bits. And the more you can put the pieces of code close together, the better, the faster it runs. And so we did some work on binary layout. This is just sort of the optimization highlights. We've done a lot of work. Okay, so this is algorithms and data structures, and we're going to pop back up into reality. Like, we are actually humans on a human's time scale. This is sort of the computer science-y things that we've done. But the other side of the coin is that you actually have to do tuning. Right? And tuning is not like going to give you big fat wins. Any system that's mature is going to have all the low-hanging fruit pretty much harvested. And if you have to make it much, much faster and you're doing it 1% at a time, it can feel like it's going to take a long time. So the question is, how do you make a lot of small changes and do it in a short amount of time so you can feel like you're actually getting somewhere? And how we've sort of stumbled along into this process is an interesting story. In 2012, we were running a different system. We didn't have the virtual machine. The virtual machine was a new idea, and it had been in development for, I believe, around 2 years at the time. And it needed to be faster than the old system in order for us to put it into production. Otherwise, Facebook gets slower. And at the time, early in about April of the year, in 2012, HHVM was 3 times slower than the current system. So we had to triple the speed of the VM by the end of the year, or else we couldn't go into production. And it had already been in development for a long time, and there was sort of some built-in peer pressure and desire to get this thing into production. And we had to basically double or triple the performance to get there. We worked on algorithms, we worked on data structures, we got the HHVM array pretty good, like I showed you in that middle diagram, and so on. But by October, we weren't going to make it, right? There was a curve we could tell we were just not going to make it. As we needed to change our behavior, and we basically needed to pull out the stops and get there. And so we just went on a wing and a prayer and said, we are going to get there 1% at a time. If you have 10 people and you can do 1% per week per person, that's like compounding interest, right? So you can actually 30 or 41% changes, which you can do with 10 people in 6 weeks. You can actually do it. The thing you have to do, though, is you actually have to do them in short time frame, right? So each change is small, but if you can just crank through them really fast, you can make a big difference. And so we basically moved ourselves to a different part of the building, and we basically put up just brainstorm, like all our ideas. Like we have a lot of ideas for if you tweak this, if you tweak that, if you shave a cycle here, if you shave a cycle there. At scale, these all might add up to something. But what we didn't want to do was, there's this decision bias where you decide to spend your time working on something, and then you become committed to making it work and succeed at all costs. And when that takes a week or 2 weeks or 3 weeks, it's a real bad idea. So the idea is we would limit the time we would spend on any given idea to 1 to 2, 3 days, and then just basically try to try out as many ideas as we could. Because what we're really doing is searching for the wins. And so we kick it off by brainstorming, right? No idea is out of bounds. What if I tweak this? What if I tweak that? One of these says, what if I optimize the set all instruction? What if I, this is my own handwriting actually, what if I try out inlining? Here's another thing. So we basically threw them up on a whiteboard, and in order to sort of have some sense of organization to it, there's sort of 2 axes, right? There's how long do I think it's going to take, 1 day, 2 days, 3 days, and how big of an impact is it going to have? And all the best ideas, hopefully, would be at the top left, because they'd be like 1-day ideas that have a maximum impact. But those are the easy ones. Like, those are already done. So you see most of these things on the lower right because they take some time, and we don't know how much impact they're going to have. So the objective of this game is to just crank your way through them as fast as possible. And each time you make something work, you put it on the win column, and your performance goes up a little bit. And if it didn't work, you put it in the negative column, and it's just there to remind you to not try that again later. And you want to iterate really fast. You've heard a lot about iteration today, but this is what we did, right? Iterate fast. And the tool we use for iteration, this is just a screenshot of it, but basically we've got this nice tool that can replay traffic on our virtual machine and then just tell us at a real fine-grained detail whether it used more instructions or less instructions, and so on. So we could do these rapid A/B experiments. Each one would take like an hour, but you could try a bunch, you could put them up, you could work on something else while you're waiting. And this would give us really good directional feedback, multiple changes per day, whether they're a good change or a bad change. So it was our way of filtering out the good from the bad. And that's the result, right? So you just crank. Right there in the middle, we found a nice big juicy win that had to do with binary layout, and we all rejoiced. And then we went back to cranking some more. And then we had another good idea for something more related to binary layout. Crank, and we got over our goal line. So this chart we've done this 3 or 4 times, and this was the most recent time, but this got us over the line to actually let HHVM go into production. And it worked so well that we did it again 6 months later, not because we were going to miss a goal, but just because we felt like that was a useful exercise. So spend time doing the hard stuff, and then spend time doing some tuning, and then spend some more time doing some more hard stuff, and then do some more time. So we're in this rhythm now for about 2 years where we do hard stuff, and then we tune, we take a vacation, go back, do some more hard stuff, do some more tuning. And that's a fun way to work, I think. It gives you an outlet for that immediate gratification, but it also gives you time to do the hard stuff. So with that, I think we have a few minutes left for questions. Do we? No time for questions, I'm told.
Sorry, we have to move on. But all of the HHVM and Hack team afterwards, talking about how we redesigned our Messenger app. So we'll see you all back there for that. Thank you very much.